previously we looked at nucleophilic substitution reactions and halogenoalkanes. This time we're looking at elimination reactions. So we need to ask ourselves, why do elimination reactions occur? And that's due to a change in conditions. For elimination reactions to occur, we need hot ethanolic conditions. And I can hear you say, what does that mean? It means that there's no water present. We're still using hydroxide ions, but due to these hot ethanolic conditions, the hydroxide ions act as a base. Remember, a base is a proton acceptor. So we're going to take the reaction of bromoethane and hydroxide ions. Here's our bromoethane. Here's our hydroxide ion, still with its lone pair. The lone pair is going to attack one of the hydrogens surrounding the carbon not attached to the bromine. And then what you'll find happens next is the electrons from the carbon-hydrogen bond move to form part of a C double bond C. And we're going to lose this bromine. It's going to be eliminated as a halide ion. So the key difference here is in an elimination reaction, because you're eliminating an atom, you're going to introduce a double bond. And actually we go from bromoethane to ethene. Don't forget your byproducts, and there's your halide ion. So elimination reactions in halogenoalkanes produce alkenes. And you can see that the carbon in the CX bond, in this case the X is bromine, goes from having 4 bonds attached to just 3. And that means that one must have been eliminated. Now these elimination reactions occur more readily in secondary and tertiary halogenoalkanes. So remember, that's when your carbon is attached to 2 carbons, and then the tertiary halogenoalkane is when that central carbon is attached to 3 carbons. So elimination reactions are far more likely with secondary and tertiary halogenoalkanes. If you have a primary halogenoalkane, it's more likely to partake in the nucleophilic substitution reactions we met earlier. Do be aware though that a mixture of isomeric products is sometimes possible in an elimination reaction. I'll show you how now. So we're going to start with 2-bromo-2-methyl pentane. There's our halogenoalkane. So we have 5 carbons in a line. We've got bromine on the second carbon and a methyl group on the second carbon. Just to point out, look, that central carbon there is attached to 3 carbons, so it's a tertiary halogenoalkane. So to show how isomeric products may be formed, I'm going to show you what happens in this case when the lone pair attacks this hydrogen here, forming the double bond down there, and we lose this bromine. So there's the formation of our double bond. Then continue the chain. So in this case, let's name it. The longest chain has 5 carbons. The double bond is on the first carbon, so it's pent-1-ene. And then we have a methyl group on the second carbon, so it's 2-methyl pent-1-ene. But let's take scenario 2 with 2-bromo-2-methyl pentane. So we have 2-bromo-2-methyl pentane again. But this time, rather than attacking this hydrogen here, I'm going to attack this hydrogen over here. So my double bond will form here instead. So because it attacked a different hydrogen, in this case, we have formed 2-methyl pent-2-ene. And do draw that full displayed formula if you're not sure how I'm naming that. So we can see what's happened here is that because our halogenoalkane was asymmetric, a mixture of products can be produced depending on which hydrogen is removed. And don't forget that our conditions here are hot and ethanolic. Haloalkanes are used in the synthesis of other organic compounds. Hot concentrated ethanolic potassium hydroxide reacts with 2-bromo-3-methylbutane to form two alkenes that are structural isomers of each other. The major product is 2-methylbutuene. Name and outline a mechanism for the conversion of 2-bromo-3-methylbutane into 2-methylbutuene according to this equation. So the name of the mechanism, it's an elimination reaction. So let's start by drawing 2-bromo-3-methylbutane. Here's our hydroxide ion. You do need to bear in mind your final product to make sure that you are actually making 2-methylbutuene, so that will dictate which hydrogen the lone pair attacks. It will cause the formation of the double bond there, and we'll lose this bromine. That will be eliminated. So to draw the product, here's our double bond forming, and then everything else remains the same, noticing we've lost the bromine. And here are our remaining products, including the halide ion. So just to double check, have we produced the right product? 4 carbons, the double bond is on the second carbon, yes. So there's our butuene, and the methyl group is on the second carbon. Draw the displayed formula for the other isomer that is formed. Okay, so let's attack a different hydrogen. How about if we were to attack this hydrogen over here? Well, then you'd get your double bond forming here. And then state the type of structural isomerism shown by these two alkenes. Well, the functional groups moved along, so it must be positional isomerism. Reaction of A with hot ethanolic potassium hydroxide gives alkane C. This is A, by the way. Name the mechanism, state the role of the hydroxide ions, outline the mechanism using structure of A shown, include the structure of the product C. So it's elimination. I already taught you previously that the hydroxide ions in this case are acting as a base. Here we're going to outline the mechanism. Look for where your halogen is attached. I'm going to attack this hydrogen here using the lone pair. There's my curly arrow, causing the double bond to form here, and we'll lose the chlorine. It will be eliminated, and then just replace your atoms. Here's your double bond. That hydrogen remains.